Hello and welcome back to the reading of the instruction manual as it is written in the Cosmos. We're on chapter 5, further analysis. We'll just jump right in. Section A, introduction. In the verification of a scientific model, it is necessary to widely explain a vast array of phenomena. Given the amount of data that we have accumulated across history, this is a very rigorous process. As the gist of the model has been explained hitherto, this chapter is supplemental material to demonstrate the wide range of observations that the model sheds light onto. Explanations are herein intended to be short and to the point where possible. As the universe is infinite, there is always more that can be considered, and this is not meant to be an exhaustive list of answers to all possible questions. No one individual could possibly be expected to consider all known observations that each person feels pertinent. Due to the nature of the model, being philosophical and deductive and using careful logic and reason, where it is capable of providing simple answers to many unanswered questions in science, it would be an undue burden to have to provide a complete model that explicitly explains every single thing. Rather, because the model is simpler than all other standard models and arguably cannot be simpler, the model speaks for itself in deserving open consideration by society at large to determine these explicit explanations. Due to the logic that if it is true, then it is true, a vast array of observations have been carefully analyzed to consider if and how they fit into the model. Important to note, in instances where it is not immediately apparent, this does not mean it is not the case. In the same way as how the speed of light was recognized to not be instantaneous by holding confidence in Newton's laws, this model cannot immediately answer everything without thought. The question becomes how. At times, that answer is not immediately apparent. However, what it does provide is a framework by which all observations can be carefully considered. The order in which questions are answered is not always the order in which they are asked. As the model has been generally described, we will now further analyze observations in light of the model. Section B, the ether. In 1887, Albert Michelson and Edward Morley performed an experiment as shown in Figure 30 in an attempt to detect variations in light traveling through the quote ether, the name assigned to unseen particles that fill the vacuum of empty space. This experiment's negative results are held as critical evidence that the ether does not exist, supposedly conclusive proof. In this experiment, light was transmitted from a laser through beam splitters which separated the light into perpendicular directions. Then the light was reflected by a mirror and came back to the source area where it was detected to determine if there was a delay caused by the presence of the ether's flow in a particular direction along the surface of the Earth, which would be observable as interference. This experiment produced a null result and has been referenced as a proof that the ether does not exist. However, there are several issues regarding the experiment. Firstly, would the ether not also obey gravity? In other words, it is an assumption that the ether would flow specifically in the direction parallel to the Earth's surface rather than being pulled towards the center of gravity perpendicular to the ground. Such a perpendicular flow would influence all light traveling parallel to the ground equally and thereby produce no detectable influence. In fact, this is supported by the shape of Earth's electromagnetic field, which extends perpendicular to the ground. Therefore, For at least this reason, the experiment did not result in detection of an ether. However, there are several examples of evidence in favor of the ether in science. Dark matter, the Higgs field, the electric field, the magnetic field, and all other fields are all examples of modern-day ether language. Indeed, if we look to the electromagnetic field, which is made of part of the ether, and ask, how does light behave in an electromagnetic field, we will find that it is directionally dependent, as stated by Pell et al. Quote, in the presence of external crossed electric and magnetic fields, E and B respectively, the light velocity is no longer isotropic, whatever the propagation medium. In other words, this experiment tells us that the velocity of light depends on the ether, as it has been shown previously that electric fields and magnetic fields are particulate in nature and are formed of part of what is effectively known as the ether. Section C, the double-slit experiment. The double-slit experiment is one of the most renowned experiments in all of physics. It is also the origin experimentally of the field of quantum mechanics, having been performed first in 1805 by Thomas Young. In a way, it is to quantum mechanics what the observation of all distant redshifted galaxies in all direction is to the Big Bang. In the same way, if the entire model finds its basis in a specific experiment, then that experiment, explained in a simpler way, draws into question every interpretation that followed. In both cases, the observations are the cornerstone upon which their respective theories are built. When the bottom is taken out from underneath something, the whole system can fall. The experiment can be conducted with a wide range of particles. Light, electrons, atoms, and even complex molecules have been transmitted through the double-slit structure to determine what interactions are occurring. In Figure 31, electrons are depicted. So two slits, we basically send particles or electrons, light, whatever it may be, through the slit and then determine what happens caused by this slit structure on a screen. The question is, what is causing this? This is known as an interference pattern, the result of two waves interfering, where there's spots where they exist and then gaps where they don't, is an interference pattern. The result of two waves interfering. The proposition is that if the systems passing through the slit were truly particles, then they would create two distinct areas on the screen where they are observed a particulate pattern rather than produce an interference pattern. Many experiments have been conducted, including transmitting single particles at a time through the slits, still resulting in the same pattern. It has therefore been concluded that everything from light all the way up through complex molecules has a wave-particle duality characteristic. Looking at the experiment through the infinite universe model, there are several factors that have not been accounted for. In particular, the interference pattern does not just happen at any slit width. Rather, the slit has to be extremely narrow. Moreover, larger particles, such as molecules, have to be projected through the slits at lower and lower velocities in order to arrive at an interference pattern. This combination provides a first clue. In particular, the narrow slit means that the particles passing through the slit are physically proximal to the slit material. As has been the theme of this analysis, this observation is considered with respect to gravity. If light is made of particles, these particles then must pass physically near either wall of the slit and due to the proximity of the particles to the slit, they would be capable of being gravitationally lensed as they pass. This is further supported by the need for higher weight particles to travel at lower velocities in order to achieve interference. Low weight particles can be lensed more easily than higher weight particles if both are moving at the same velocity and influenced by a given system. To account for this, it is necessary for the particle to physically travel slower so it is exposed to the local gravity of the slit material as it passes for a longer period of time to actually lens the particle's path and thereby produce an interference pattern result. Additionally, it is important to note that there are always smaller particles, and our actual capacity to perform this experiment without using many particles simultaneously inadvertently, which behave as a cumulative wave, is very low. Arguably, it is impossible in the same way as a perfect vacuum cannot be created. A single particle cannot be isolated without bringing with it ever smaller and less detectable particles that can influence observations. Moreover, single particles projected through double slits, as done in the single photon double-slit experiment, would be gravitationally lensed one at a time by positioning passing through the slit materials and would ultimately arrive still in an interference pattern. This interpretation requires no counterintuitive additions to the model, but rather uses the same basic premises of all previous interpretations to provide an explanation that is reasonable and logical. The photoelectric effect. The photoelectric effect is defined as the emission of electrons or other free carriers when light is shown on a material. The emission of electrons by radiation requires the energy of the radiation to reach or exceed a threshold frequency. Below that level, no electrons are said to be emitted regardless of the light intensity or the length of time of exposure to the light. Albert Einstein proposed that a beam of light, therefore, is not a wave but rather is a collection of discrete packets, photons. Dependent on how strongly the electron is held to the system, the photoelectric effect can require photons with energies approaching zero when electron affinity is negative. For core electrons and elements with a high atomic number, on the other hand, the required energy can be above 1 mega electron volt. Again, we can analyze this with the above infinite universe approach, which arrives at the argument that different wavelengths in the electromagnetic spectrum are waves made up of different masses of particles. Lower energy light is made up of relatively low mass particles. When we shine high energy radiation onto a surface, we are ultimately radiating the atoms of that surface with larger mass systems having a higher energy density because there is more mass per volume, a higher density, in more energetic light. For consideration, we can envisage a matter wave hitting the planets of the solar system. If the wave is low in density, it will not influence the planets substantially. If it is high in density, it could physically push the planets into different orbits, or out of the sun's orbital entirely. This is effectively what is happening with the photoelectric effect. The radiation acts as a wave of particles physically pushing against the object. If the particles are low in mass, it acts as a gentle wind which can only dislodge the least bound of systems. At a sufficiently high energy, the wave of light acts like a tidal wave on an electron and can be able to effectively push it out of orbit. Whether or not the strength is sufficient depends on all forces on the electron. If it is closer to the nucleus of a heavier atom, then it is more strongly bound, just as gravity would explain. This is why electrons are able to be dislodged from atoms when light is shown on a material, and why there is a threshold frequency, and why the photoelectric effect behaves as it does. So we're going to take a break here, and in the next video we'll jump into the rest of this chapter, and on we go. Thanks.